Okay, so let us see this next result that we have already talked about in a previous Galois theory video. Namely, that if K is a finite extension of some field F, then the group of automorphisms of K relative to F is finite and its number of elements, that is its order, is at most the degree of K over F. And let us also recall that this is the group of those automorphisms of K under each of which all the elements of F stay fixed, that is, they do not change. Alright, so let us now see the proof. So in the proof, we give this some name, say we call it N. Let the degree of K over F be N. This means that as a vector space over F, K is n-dimensional. Now, unlike the general case, that is where you have any vector space over any field, the dimension can be 0 also. However, in this case, the least value of n is 1, and that will happen when K is equal to F. So that means n is a positive integer, and there is a basis of K over F having n vectors. That's what it means. So let's also consider one such basis. Let u1, u2, un be a basis of K over F. Now we want to prove this inequality. Suppose it's not true. So that means what? That means that the number of elements in this group is greater than this number. Now that supposition has in it also the possibility that the group is infinite, and from this supposition we are going to derive some kind of contradiction. So if the number is greater than n, then we are going to get at least n plus 1 distinct elements in this group. Whether the group is finite or infinite, the supposition that this is greater than n is going to get us at least n plus 1 distinct elements. So that, in fact, that itself we are going to suppose. Suppose there are distinct elements sigma 1, sigma 2 and so on up to sigma n plus 1 in this group. So all of these are automorphisms of K, and under each one of them the entirety of the field stays constant. Alright, so now we are going to consider a system of homogeneous linear equations. Consider the following system of inhomogeneous linear equations in the n plus 1 unknowns. Okay, so these are the unknowns. The number of equations is going to be n equal to this dimension, but the number of unknowns is 1 more than that. Let's see what the equation, the system is. So what we are going to do, we are going to get one equation for each basis vector here in this manner. On u1, we first apply the first automorphism sigma 1. Now u1 sigma 1 is going to be what? u1 sigma 1 of course is the image of u1 under sigma 1. This is going to again be a filled element in K. So that we take as the coefficient of x1. Then on u1 itself we apply the second automorphism sigma 2, and that we make the coefficient of x2, and it goes like this. So the last term will be obtained like this by applying sigma n plus 1 on u1, and that becomes the coefficient of xn plus 1 equal to 0, because we want a homogeneous system. Each equation is going to have the right hand side equal to 0. So like that, the next one will come from the filled element u2, and the next one will just be this u2 sigma 1 x1 plus u2 sigma 2 x2 and so on, plus u2 sigma n plus 1 xn plus 1 equal to 0. You see, it's very easy to make mistakes in writing this system, so we have to be careful. And like this we get other equations also for the subsequent ui's. And finally, so these are the other intermediate equations in the system, and finally we are going to get one for the last vector un sigma 1 x1 plus un sigma 2 x2 plus un sigma n plus 1 xn plus 1 equal to 0. Now we know from linear algebra a basic fact about such equations. I mean, for such systems where the system is homogeneous and there are more unknowns than the number of equations. And the fact is that such systems have non-trivial solutions, that is, solutions in which not all the xi's are equal to 0. The solution in which all of them are equal to 0, of course, is a solution. We already know that because the system is homogeneous. If you take all the xi's equal to 0, that will obviously be a solution. But in this kind of situations, you have a non-trivial one also. From linear algebra, actually we have already got this result as theorem 433. This is the third section of the chapter on vector spaces, that is the fourth chapter. If you remember, there we had the notion of linear functionals, that is linear transformations from a vector space into the underlying field, and results from that section were applied to such systems, and we got this this result. So by this theorem, there exist filled elements an plus 1 in K, not all 0, such that these numbers, if you substitute them respectively for the xi's, are going to solve all the systems. That means ui sigma 1 a1 plus ui sigma 2 a2 and so on plus ui sigma n plus 1 a n plus 1 is equal to 0 for all these values of I. Alright. Now we are going to use the fact that these ui's are actually the basis vectors for K as a vector space over F. And that's why every element of K is a linear combination of these ui's and where the coefficients come from the underlying field F. Now, for any element T in K, there exist scalars alpha 1, alpha 2 up to alpha n in F such that T is this linear combination alpha n un. Alright, so now we have two things. Two things means we of course have T in this form and we additionally have this thing. This thing means actually you are looking at n relations, n equations actually. Now, how can we use these things with this T? Let's see. That will get us a contradiction. A contradiction we will get which to claim that what ultimately we are going to get is a contradiction, we have to recall a previous result from this section itself. But let us see where it takes us. So, what we do is this. Let us see what this becomes. You see the form of these relations. Here you have ui. So what now I am going to write is, in place of ui I am going to write t. Everything else will be like this. So t sigma 1 a1 plus t sigma 2 a2 and so on plus t sigma n plus 1 a n plus 1. I am not going to write equal to 0, not so fast. This is my claim. Okay, I want to show that this expression becomes 0, and I have to next use this linear combination in place of t. So it's going to be a little big, but let's just see where it gets us. So first what we are going to do, we will apply sigma 1 on this linear combination, and keep in mind that sigma 1 is an automorphism of K, and all these things you are seeing ultimately are elements of K. I mean, of course the alpha i's are coming from F, but ultimately they are also in K. So if you apply sigma 1 on this linear combination, you are going to get this alpha 1 sigma 1. I will be a little slow in writing because we can make mistakes very easily, plus u1 sigma 1 plus alpha 2 sigma 1. We should not forget we are applying sigma 1 only. Alpha 2 sigma 1 u2 sigma 1. Right now we are applying sigma 1 only, plus finally un, alpha n un, alpha n sigma 1 un sigma 1, and this sum is just t sigma 1. Outside you have a1, and we are going to do this with the second one also. So I think it's better to do it here on that side. So next we will apply sigma 2 on this sum. Okay, only sigma 2, fine, plus alpha 1 sigma 2 u1 sigma 2 plus alpha 2 sigma 2 u2 sigma 2 plus alpha n sigma 2 u1 sigma 2, and we have a2, and like that we have other terms as well, plus, and then this final one. Here we are going to apply sigma n plus 1. u1 sigma n plus 1 plus alpha 2 sigma n plus 1 u2 sigma n plus 1 plus alpha n sigma n plus 1 u1 sigma n plus 1, and outside we have multiplied with this a n plus 1. And the next, very next step of course is to apply the right distributive law and multiply a1 with all these things. Say we do that, okay. Similarly here we multiply all these terms by a2 on this sum by a n plus 1, and all the intermediate sums as well. And then after doing that, you note that you have got some things, some terms where you have some other things which you can take common as common term outside. You see, from this term you are going to get alpha 1 sigma 1 u1 sigma 1. Oh yes, but there is one more step I forgot entirely. Yeah, before you can do that, I mean you can multiply all the terms by a1, but before that there is one more thing. Note that all these sigma i's are automorphisms under which f is constant, that is any field element coming from the underlying field f, it does not change, and these alpha i's are in fact coming from the underlying field. So there will be one more line before we do anything else. This alpha 1 sigma 1 will be simply alpha 1 because it's not going to change under sigma 1. u1 sigma 1. Similarly, alpha 2 u2 sigma 1, like that alpha n un sigma 1 a1 plus so the next term means this chunk is alpha 1 u1 sigma 2 plus alpha 2 u2 sigma 2 plus alpha n un sigma 2 A2. And similarly, the last sum is also going to be simplified like this. U2 sigma n plus 1 plus alpha n un sigma n plus 1 a n plus 1. Yeah, now only we can talk about that application of the right distributive law. So say you do all the multiplications also. You multiply all these things by a1 and so on. So you are going to get some terms first. You get alpha 1 u1 sigma 1 a1. From the next chunk you get alpha 1 u1 sigma 2 a2. And like that you keep on getting terms from all the first terms of these chunks. All of them contain alpha 1. So you can take alpha 1 outside using the left distributive law. If you do that, you are going to get something like this. Alpha 1 times u1 sigma 1 a1, u1 sigma 1 a1 plus alpha 1 times u1 sigma 2 a2 and it goes like that. From the first term of the last chunk you get u1 sigma n plus 1 a n plus 1. All of these terms contain alpha 1 in them. Like that, from the second terms of all the chunks you get alpha 2, and along with that this time you consistently get u2. On u2 you are applying all the sigmas. On u2 here we have applied sigma 1, sigma 2 and so on, sigma n plus 1. So this time we are going to get u2 sigma 1. Do not forget that we have still a1 with the first one, a2 with the second one and so on. u2 sigma 2 a2 plus u2 sigma n plus 1 a n plus 1. This is only with alpha 2, and it goes on like this with the other alphas. Eventually we consider the last terms of all the chunks. From all of them we have alpha n, which we can take outside, and that is going to get us un sigma 1 a1 plus un sigma 2 a2, and this very last term of the last chunk gives us un sigma n plus 1 a n plus 1. Now you go back to those relations that we wrote after writing that system has a non-trivial solution. If you go back to those relations, you will see that there you are getting these terms, these sums. This one is equal to 0, this one is equal to 0, and like that finally this one is equal to 0. So that's how, let me write here itself. You get alpha 1 times 0, alpha 2 times 0 and so on. So this is 0. Okay, so what is it that we have shown? Because we have had to erase the things, I have to write the entire thing once. Entire thing means, let me write what it is that we have shown is equal to 0. that is T sigma 1 A1 plus T sigma 2 A2 like this n plus 1 is equal to 0. However, T was any arbitrary element of our field K. So that means we have shown that on any element, if we apply this structure, this thing, if we apply all the sigma i's in this manner and multiply the results respectively by these ai's, then that sum becomes 0. However, this is not possible, and the result it is contradicting is theorem 561. Theorem 561 says that if we have distinct automorphisms, okay, of a field K, where the under those automorphisms the elements of F they remain the same, then this cannot happen for all the elements T in K. But this contradicts theorem 561. So our supposition is wrong. What was our supposition? Namely that we will find n plus 1 distinct elements in the group. So that is not possible, and that is why first of all the group has to be finite. Okay, because if it is an infinite group, then of course we will find n plus 1 distinct elements, but that is not possible. So the group has to be finite, and that too the order has to be less than or equal to n. So that's how we have the proof of this result. Now this result can be used, of course, to say further things in Galois theory. It's an important result, but in fact it can also be used to answer some questions about symmetric rational functions. In particular, a classic result about those objects we are going to get as a consequence of this result, and that result in turn is going to help us further in delving deeper into Galois theory. So we will see these things in the next field theory update, and tomorrow of course we have our usual upload as well. So see you tomorrow with calculus. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.